Good day, I'm Smriti Mahajan. Today we are going to talk about galaxies and their large scale distribution in the universe. Now we know that there are primarily two kinds of galaxies in the universe, the ellipticals and the spirals. We live in a spiral galaxy called the Milky Way, which is a massive spiral with stellar mass of the order of a few 10 to the power 10 solar masses and H1 mass of a few times 10 to 9 solar masses. Although we haven't left the galaxy to take a selfie with it, we believe that the Milky Way would look something like the picture on the right here. This is a scientifically recreated image based on our observations of other galaxies and the distribution of objects within our own galaxy from our position around 8 kiloparsec from the galactic center. Since we are in a spiral arm, we see a lot of dust and stars in one part of the sky while there are only some stars in other directions. This is the plane of the Milky Way as observed from the northern hemisphere from the island of La Palma in Spain. This is another view of the Milky Way from the southern hemisphere. The building that you see in the front of this image is the Cerro Tololo Inter-American Observatory, the CTIO Astronomical Observatory, located in northern Chile in La Serena, about 80 kilometers from La Serena. The two blue objects that you see on the left in this image are what makes the southern skies much more special than the skies in the northern hemisphere. These two are the two satellite galaxies of the Milky Way, the large and the small Magellanic Clouds. Massive concentrations of many tens and hundreds of galaxies bound together by gravity are called clusters of galaxies. Now, there is no hard boundary between clusters and groups, but groups can be as small as a triplet of galaxies, while clusters are generally much larger and have many more galaxies in them. Clusters and groups also contain a large amount of dark matter. They also contain X-ray emitting hot gas called the intracluster medium. You will hear more about this X-ray emitting gas from Professor K.P. Singh. Locally, our Milky Way is part of a concentration of around 50 galaxies or so called the local group. Milky Way, as of today, is known to have about 50 satellite galaxies. Our largest neighbor is the Andromeda galaxy that you can see on the right of this image. Andromeda is slightly bigger than the Milky Way and is approaching the Milky Way with a speed of about 125 kilometers per second. Simulations suggest that Andromeda and Milky Way will have a head-on collision in about 4 billion years from now. Milky Way and Andromeda are separated by a distance of about 6 megaparsec, which is the typical distance between large galaxies in the universe. In other words, one can imagine that the space is largely empty. An important point to note here is that this information that I shared with you on this slide was not known to us even 100 years ago. That is, the study of the distribution of galaxies is a recently emerged field in astronomy. Our universe is laid out such that all matter is distributed along large-scale filaments on which the galaxies lie. In this image, you see the dark matter distribution, but the luminous matter should also follow this same distribution. This understanding that the universe is very filamentary is only current knowledge. We did not know this 40 to 50 years ago from now. What you are seeing in this image is the distribution of prominent galaxies, the nearest cluster called Virgo, and the filaments in our local neighborhood. We believe that most galaxies may form on filaments and then move towards the dense clusters and groups due to gravitational attraction. This slide also shows you the currently accepted idea of the hierarchical formation of structures in the universe, wherein the smaller objects come together to form larger structures. So far, we have seen the large scale distribution of dark matter, but this is what we observe. This image shows the distribution of galaxies in a slice cut out from a three-dimensional universe. Each point in this image is the position of a galaxy color-coded by its optical color. Notice that the distribution of galaxies is indeed very filamentary as far out as you can see from the Earth. In this case, the Earth is at the center of the circle. We still do not know a lot about these filaments, their scale, their properties, and so on. So cosmographic mapping of the universe is a big business now. Just like 400 years ago, we were trying to name countries and continents on Earth. Now we are doing the same by discovering large congregations or structures in the universe. It's in the last 20 to 30 years that we have discovered superclusters and then decided to call them by names such as Coma, Lanakia, Shapley, and the latest addition to the list being Saraswati. This enormous structure was discovered by a group of Indian scientists from the Inter-University Center for Astronomy and Astrophysics. Saraswati is surrounded by a network of galaxy filaments, clusters, and large voids. Voids are large empty regions in between the filaments. The main body of the supercluster comprises at least 43 massive galaxy clusters at a mean redshift of 0.28 and a total mass of about 2 into 10 to the power 16 solar masses. These results were published by a team of scientists led by Professor Bagchi from IUCAA, Pune. In the 1920s, when Edwin Hubble started comparing the redshifts of nearby galaxies to their redshift independent distances, for instance, distances measured using the supernova type 1a, he found the trend shown on the right figure here. That is, the farther away a galaxy is from us, the faster it is moving away, suggesting that the universe is expanding. This relation between the radial velocity and distance of galaxies is known as the Hubble-Lemaître law. But we just saw that galaxies are held together by gravity. Hence, this observation that the universe is expanding implies that the galaxies are moving away from each other because the space as a whole is expanding. Just like this analogy, where a cake batter with raisins in it expands due to some rising agent, as a result of the expansion of the dough, the distance between the raisins increases. The raisins here are galaxies and the dough is the space at large. But the problem in this picture is that the raisins in the dough cannot move on their own, but galaxies can move due to gravity. Remember, I told you that Milky Way and Andromeda are coming towards each other due to gravitational attraction. Around the same time, when Hubble discovered this relation, the theorists working with Einstein's theory of relativity found that there are two solutions to the equation governing the dynamical state of the universe. The universe can either expand or contract. Hence, together with the observational evidence of the Hubble-Lemaître law, we figured that the universe is expanding is the more plausible solution. The constant that connects the two sides of the formula is called the Hubble's constant and is measured in units of kilometers per second per megaparsec. The line that you see fitted here in the plot has a slope of 72 kilometers per second per megaparsec. But notice that the data points do not lie exactly on the fitted line of regression, implying there is more to this relation than that meets the eye. These tiny deviations of the data points from the fitted straight line are caused by gravitational pull on a galaxy, such that locally a system can collapse or attract even though the surrounding space is expanding at large. For instance, the Andromeda and the Milky Way are coming towards each other despite the universe expanding at large. So they have decoupled from the larger space. Its gravitational pull can also be due to the invisible dark matter, which does not emit light. Hence, by measuring these deviations from the Hubble-Lemaître law, called the peculiar velocities of galaxies, we can learn about the distribution of dark matter in the universe. But this has been founded only in the last 25 to 30 years, when we have discovered very accurate ways of measuring distances to galaxies very far away. Now, I have already talked about the relation between the morphology of galaxies with environment. This image shows the fraction of elliptical and spiral galaxies, also S0s, as a function of the projected galaxy density on the x-axis. Alan Dressler found that the fraction of spiral galaxies increases while that of elliptical galaxies decreases as the density of the environment decreases, implying that there are more elliptical galaxies in denser environments, such as clusters and groups. Whereas as one starts moving away from the centers of clusters and groups, the fraction of spiral galaxies begin to increase. This is the most cited proof for the evolution of galaxies with environment. However, in 1980, when Alan Dressler discovered this result, it was unknown as to what leads to this evolution. Now, the morphology has been replaced by more quantitative measures of the classification of galaxies, such as their star formation rate or the proxy for the same. In this image, the y-axis shows the fraction of galaxies having equivalent width of H-alpha line in their spectra greater than 4 angstrom. In this particular study, equivalent width of H-alpha equals 4 angstrom is considered as the minimum H-alpha emission a star-forming galaxy should have. And as expected, as Alan Dressler found, the fraction of such star-forming galaxies increases with decreasing environmental density. Various phenomena can lead us to the observed relations between the properties of galaxies and their environments. These are collectively called environmental processes. Now let me introduce to you some of them here. One obvious way of creating elliptical galaxies is by merging two spirals. This montage of different systems, all of these are Hubble images, actually show the sequence in which a merging pair of galaxies will evolve to form a large elliptical. When a galaxy falls into a cluster, it experiences the ram pressure force from the hot intracluster medium. The image on the bottom left shows the radio contours of the galaxy overplotted on the optical R-band image of this galaxy. And as is obvious, it appears that the gas is being pushed towards the top right as the galaxy falls towards the center of the cluster, while the one in the center shows how the dust lanes are moving upward due to the force of the medium experienced from the bottom. The image on the right is a sequence from a simulations showing the side view of a disk entering the cluster halo and showing how the medium disrupts the disk. Here is another extraordinary example called serendipitously. This is the galaxy C153 in a cluster called Abell 2125 at a redshift of 0.25. Here is the same galaxy in different wave bands, and what you see is that all the gas which is being pulled out of the galaxy as it rams through the intracluster medium is heated up when it encounters the intracluster medium and is shown here in this purple color. Here is another example of ISO 137001 in the cluster Abell 3627, which shows a 70 kiloparsec long tail with a gas mass of about 10 to the power 9 solar masses coming out of a galaxy, again, which is falling through a cluster and experiencing the effect of the intracluster medium. Now, strangulation is an interesting mechanism whereby the warm gas halo acting as a reservoir for the cold gas in the galaxy disk gets stripped. Now, rather than the cold gas in the galaxy being stripped off, as in the case of the ram pressure stripping. As a result of strangulation, the star formation in such a galaxy will decline on longer timescales because stars still continue to form from the cold gas which is present in the disk. But new gas, which was earlier condensing from the hot halo, is not condensing anymore. As a result of strangulation, the reservoir of cold gas is being stripped from the galaxy. Galaxy-galaxy harassment is very important in intermediate density environments such as filaments and the outskirts of clusters. In such regions, two galaxies can come close enough to gravitationally influence each other and may even cause morphological distortions. But due to several reasons, such as the presence of strong unidirectional fields along the filaments, they do not merge. Such encounters may perturb the gas clouds in a galaxy, therefore igniting a burst of star formation. But although the relative velocity of such strong encounters could be as high as around 1500 kilometers per second, the velocity impulse internal to the galaxy is of the order of less than 50 kilometers per second. As a result, by the time the perturbation in the disk becomes visible in the form of decline in star formation or some other means, the interacting galaxy which had perturbed the galaxy has already moved much farther away. Once again, I would like to stress that multi-wavelength data are crucial for the study of environmental effects in galaxies because only multi-wavelength data could throw substantial light on the various components of a system. For instance, here you see three galaxies which are part of the M81 group. But if we observe the same group in radio 21 centimeter, you see all this gas which has been thrown around due to the interactions between all of these galaxies. In fact, we also find that there is a fourth and maybe many more galaxies involved which are too faint to be visible or yet visible optically. I end this lecture here and leave you with this beautiful demonstration of hierarchical structure formation from the illustrious simulation. Thank you.